Bravanath Hessa is proud to present a new video tutorial for its MC 550 CNC and 650 CNC bending machines. We are going to show you all the new developments that come with these machines. Radius prediction. The powerful software is able to predict any radius. Axle interpolation. Pressed interpolation for enhanced finishes. Technology 4.0 for total connectivity, and Eco Mode for greater energy sustainability. All Nar Hessa machines are completely manufactured at our facilities. We'll begin by creating a sample bar with the MC 550 CNC to determine how the profile to be used behaves throughout the bending process. You choose the profile, a rectangular tube, dimensions 35 by 20 by 2. You choose the material, iron. You set up the position of the rollers and the point of contact between the material and the upper axle. You do the same process with the lower axles. Position the lower axles into the profile clamp so it's secured well. Pay attention to where the profile weld is so that it's always in the same position. Access the radius database and add the clamp point. The radius is 0 because the profile is simply being held. Go back to manual mode and access the general data page to do a velocity test. Release the encoder so it automatically goes to the operating position. Press the velocity test icon and move the joystick to the left. The profile will move in this direction until the velocity test finishes. Confirm the message. A green tick indicates the velocity test has been completed correctly. Go back to manual mode and move the joystick so the profile goes back to the starting point. For the sample bar, we are going to create a first 200mm straight section to guarantee optimal support on the roller. Use a marker to make a first mark on the profile to be bent. Put the x-axis in position 35 to create the first bend radius for the sample bar. Define a 350mm feed and press the button to get the first curved section on the bar. Make a second mark on the profile, right where the curved section ends. Put the x-axle in position 45 and define a 200mm feed to create a second straight section. Make another mark on the profile to indicate where this section ends. Put the x-axle in position 30 to create the second bend radius for the sample bar. Define a 350mm feed. Press the bend button and again, mark the point where this second curve ends. Continue with the procedure described up to this point, creating straight and curved sections alternatively, closing the x-axle in intervals of 5 by 5 to get a sample bar with smaller and smaller bend radiuses. This operation should only be done once for each profile. By simply entering 3 radiuses in the database, the machine will be able to predict any other radiuses. Put the encoder back in rest position and release the profile to analyze the sample bar. This is done to prevent the rollers from causing stress on the profile, which could alter the results. On each of the curved sections of the bar, mark the position of the x-axle where they were created. Measure and write down the bend radiuses obtained. Access the Radius database and go about creating new records by entering the data available. The adjustment accuracy is 99.95%. This indicates the radiuses were measured correctly. This guarantees excellent results with future predictions. To determine the deformation of the material during bending, use a marker to mark the exact starting and end points of the curve with the smallest radius obtained. This is done like this because this is the curve with the most deformation. As can be seen, there is a difference between the marks made before and the ones we just made. To measure this, transfer the existing marks on the profile to a section of well-tensed cable. You can clearly see how the length of the curve obtained differs from the programmed length due to the material deformation during the bending process. We've gained 38 millimeters at the beginning of the curve, which had been lost in the prior section. 10 millimeters have been added at the end of the curve, which had been deducted from the prior section. The length of the curve obtained is 361 millimeters. However, the actual curve programmed had a length of 350 millimeters. This means the profile was stretched 11 millimeters for every 350 millimeters of feed during the bending process. In other words, 0.0314 millimeters per millimeter. Now, with the same profile, we are going to make the piece shown on the drawing. Access the menu, Programs, New Digital Program. Choose the profile and enter the dimensions. You choose the material. Set up the position of the rollers on each one of the machine axles. Put it in automatic mode. Add a first step to the program, the unloading step, defining the position of the lower axles to be able to remove the piece from the machine once finished. Create a second step, the loading step, defining the position of the lower axles to be able to insert the material with enough of a gap. Add a third step to the program, the clamping step, by choosing a value of 0 from the radius table so the lower axles will be in a position to firmly secure the profile to be bent. The fourth step starts the program and is always created automatically to detect the material. Create a fifth step, where you define the length of the first straight section on the piece to be made, adding the extra 38 millimeters corresponding to the beginning of the next curve to the level shown on the drawing. Sixth step. Enter the 380 millimeters radius, and the software predicts the position of the x-axle at 22.6. Create a seventh step, where out of the total length of the curve, which is 651.88, we deduct 38 from the beginning of the curve, 10 from the end of the curve, and 20.46, which is the result of multiplying the deformation per millimeter by the length of the curve. So the total resulting length will be 583.4 millimeters. Add an eighth step to the program. Again, choosing a radius of 0 to be able to create the following straight section on the piece. Create a ninth step. The length of the straight section is the sum of the level of 300 millimeters plus the 10 millimeters at the end of the prior curve plus the 38 millimeters at the beginning of the next curve. Result 348. Add a 10th step to the program. Again, Enter a radius of 380 millimeters so the software will predict the position of the axles. Create the final step of the program by following the procedures described in the 7th step. Obtaining an R-axle feed of 583.4 millimeters. Press Program and save it with the name indicated on the drawing. Finish the program and move to production mode by pressing the green icon. With Step 2 selected, press the button to move the lower axles to the material load position. Load the profile onto the machine and press the button again to move the lower axles to the clamp position. Remember that it's always important to place the weld in the same position to guarantee the profile always behaves in the same way. Adjust the position of the photocell so it detects the profile. Release the encoder so it automatically goes to the operating position. Press the button and keep it pressed to create the piece automatically. Return the encoder to the rest position and run the unloading step to remove the finished piece. Check the length of the straight section, 500 millimeters. Measure the radius of the curve created, 380 millimeters. In order for the machine to be more precise all the time, it's important to add the verified radiuses in the database. Ask the software to show the position of the axles for the radius of 380. Look at the position values obtained for the X and Y axles. Add a new record to the database. A radius of 380 millimeters, X-axle position of 22.6, and Y-axle position of 45. Go back to Automatic Operating Mode. We're going to create this new piece with the same profile and material. Go to Automatic Mode, Programs, New Digital Program, and choose the rectangular tube. Enter the dimensions, 35 by 20 by 2. Choose the material, and set the position of the rollers in the 3 axles. Press Automatic and add the unloading step, defining the position of the lower axles to be able to remove the finished piece. Create a second step, Loading Step, which makes it possible to place the profile in the machine with enough space. Add the Clamp step and define the position of the lower axles so the profile is firmly secure. The 4th step is created automatically. Step 5. Define the length of the straight section of the piece, 300 millimeters, plus the 38 millimeters at the beginning of the next curve. Add a 6th step to the program and check whether the desired radius already exists in the table. In this case, it doesn't, so you ask the software to predict the position of the axles for a radius of 280 millimeters. In the 7th step, specify the length of the first curve, 271.1. Since this one is followed by another bend at 271.1, you deduct a quotient between the curves of 18 millimeters, the result of prior testing, and the total deformation of 8.51 millimeters. Result, 244.6. Create an 8th step and check whether the radius of 1300 millimeters already exists in the table. It doesn't, so you have to ask the software to predict the position of the axles for the radius of 1300. Add the 9th step to the program, calculating the feed of the R-axle. Length of the curve, 1,896.15. plus the beginning of the next curve, 38 plus the end of the previous curve, 10, less the deformation, 59.54. Result, 1,884.6. In the 10th step, ask the software again to predict the position of the lower axles for a radius of 280 millimeters. As can be seen on the drawing, the final curve has the same length as the first. The R-axle feed for the first curve was calculated in the 7th step of the program, 244.6 millimeters. So, create the final step in the program with this same value. Save the program and move to production mode. Press the button to run the clamp step. Check that the profile is firmly secure and release the encoder. Press the button and keep it pressed to create the piece completely automatically. Check the radiuses of the finished piece and you'll see they're as expected. Now enter them in the database. In editing mode, access the radius database. It's important to emphasize that the more verified radiuses there are in this table, the more accurate the predictions will be. Now, with 6 radiuses, the adjustment is 99.95%. By adding a new radius, the adjustment will increase 1/10. And if another radius is added, the adjustment will increase again another 1/10. We're going to bend this triangular piece we had previously made and for which the program was saved. Access the menu, Programs, choose it, and load it to move to production. Press the button to place the lower axles in the load position. With the profile loaded into the machine, release the encoder so it goes to the operating position. Press the button and keep it pressed to create the piece completely automatically. Return the encoder to the rest position and run the material unloading step. Now, let's bend another piece that's exactly the same to verify the machine's repetitiveness. Completely identical and symmetrical. Let's create this oval shape. Let's repeat a second piece to check the machine's repetitiveness. As can be seen, the two pieces are exactly the same. Now, let's bend this square with the rounded vertices. Access the menu, Programs, New Digital Program, and choose the rectangular profile. Profile dimensions 25 by 15 by 1.5. Choose the material and set the position of the rollers in the 3 axles of the machine. Move to automatic mode and create the unloading steps. Load and clamp. Step 5. Add the 30 mm at the beginning of the curve to the 160 mm of the first straight section and enter them in the R field, 190. Check the radius library to check whether we have the 250 radius recorded. Choose it to load it in Step 6. In Step 7, you deduct the 30 mm from the beginning of the curve, the 15 from the end of the curve, and the 11.97 from the material deformation from the 431.97 mm, total 375. Step 8. Place the rollers at a radius of 0 to do the following straight section. Enter the 335 mm. The result of the sum of the length, 290, plus the beginning of the curve, 30, plus the end of the curve, 15. Choose radius 250 again from the library. Now you can copy the previous steps since the shape is symmetrical. Continue defining all the sections of the piece, like this, up to the final curve in Step 19. Save the program and move to production. Release the encoder and bend this piece automatically. Return the encoder to the rest position. Run the material unloading step and remove the finished piece. Check the piece measurements and confirm it complies perfectly with the specifications on the drawing. As can be observed, there is a marked transition at the beginning of the curves from the straight sections. If this is inconvenient, you can soften it with pressed interpolation, which will significantly improve the final result. In editing mode, go to Programs, choose the program, and create a copy by renaming it. Choose it and load it to be able to edit it. Access the screen with information on the program steps and edit the R-axle feed in all the straight sections, reducing the length by 30 mm. In order to later add the pressed interpolations, change Step 5 from 190 to 160. Step 9 from 335 to 305. Step 13 from 335 to 305. And finally, Step 17 from 335 to 305. Choose step number 5 and press the interpolation icon. Add a pressed interpolation 30 mm in length This time, use 4 steps. The greater the number of steps, the softer the transition will be. Choose the following straight section in step 15 of the program and add another pressed interpolation just like the previous one. Repeat the same process 2 more times, creating pressed interpolations at the beginning of the 3rd and 4th curve in the piece. Return to automatic mode and save the program. Run the program to create the piece automatically. As can be seen, before the start of each one of the curves, do the 4 steps added to create the pressed interpolations, which will significantly improve the final result. The finished piece has a better finish. You can see the enhancement in each of the transitions. With just a little experience, you can create really complex pieces, like this ellipse, by creating a consecutive series of 9 different radiuses. Let's now work with the MC650 CNC bending machine. The work process is the same as with the MC550 CNC. As can be seen, the knurled roller on the encoder is not aligned with the round tube we're going to use. To correct the alignment, you have to move the roller to the inside. To make this adjustment, raise each one of the lower axles. This will make the work easier. Use an Allen wrench to loosen the screws on both sides. Move the knurled roller until it's in the desired position. Tighten the screws on both sides. As can be seen, the knurled roller on the encoder and the round tube to be bent are now well aligned to be able to work. It's important to remember that you can set up the machine in millimeters or inches in the settings menu. In manual mode, access the general parameters and choose the round tube. Diameter 1 1/4 inches, thickness 0.09 inches. Choose the material and position the rollers over the axles. Return to manual mode. Always place the weld in the same position. This is important to guarantee the profile behaves in the same way. Position the lower axles into the profile clamp so the tube is firmly secured. Release the encoder so it goes to the operating position. In manual mode, access the general data, velocity test, and follow the instructions shown on the screen. You must only do this test on profiles that haven't been used before. If they've already been used, the test will have been saved. Adjust the photocell so it detects the tube to be bent. Place the end of the tube in the initial position, just above the encoder axle. Make the tube move forward 200 millimeters to create the first straight section and use a marker to mark the starting point of the first curve in the sample bar. Put the x-axle in 55 and move the r-axle forward 500 millimeters to create the first curve. Now use the marker to mark the end point of this curve. Put the x-axle back in 73 and move the r-axle forward 200 millimeters to create a second straight section. make another mark on the tube. This point will indicate the start of the second curve on the sample bar. Now, put the x-axle in 40 and move the tube forward 500 mm to create the second curve. Mark the final point and repeat the process described by creating straight sections and curves consecutively with variations every 15 on the x-axle. This operation should only be done once for each profile. By simply entering 3 radiuses in the database, the machine will be able to predict any other radius. With the sample bar finished and outside the machine to prevent the pressure from the rollers from altering the result, measure the radiuses of each of the curves created to enter them in the database. In manual mode, access the radius database and create a new record. Begin with the 0 radius, which represents the clamp position. Continue with the 4 remaining radiuses until all the information provided by the sample bar is completed. "99% adjustment," proving the measurements are correct and guaranteeing exact predictions. To be able to determine the material deformation, mark the exact start and end points on one of the curves, which differ from those marked previously. Transfer the existing 4 marks on the tube to a section of well-tensed cable. Looking at the results, you can see how 50 mm of the straight section is lost moving from straight to bent. In the transition from curved to straight, 9 mm are lost from the straight section. Plus, you can see how this material has deformed, stretching 10 mm for every 500 mm of feed. Therefore, 0.02 mm per millimeter. Let's create this structure for a greenhouse. When there is not enough height to make a piece all at once, you can order each bend so the finished piece does not exceed a certain height. Begin by creating the first of the legs, then the other, and finally, shaping the upper vertex. In manual mode, access the menu Programs. Now we're going to see how to do a program step by step. Choose the profile, a round 1¼ by 0.09 inch tube. Choose the material and set the position of the rollers. Go to Automatic and place the lower axles in the unloading position, X at 110, Y at 110. Press the icon to save this step and confirm. Move the lower axles to the loading position, X at 80, Y at 80. Save this second step. Insert the tube into the machine, being careful to place the weld in the same position it was in when the sample bar was created. Place the lower axles in the clamp position, 73, 73. Save the clamp step and confirm. A message will appear on the screen asking whether you wish to start the R-axle referencing. Release the encoder and press OK to automatically start the R-axle referencing. Choose the R-axle and enter 850 mm, corresponding to the sum of the length of the first leg, 800 plus 50 for the beginning of the curve. Activate the machine. Save and validate this step. Access the radius database and ask the software to do an estimate for a radius of 360 mm. The prediction indicates the position of the x-axle, 25.4. Go back to the automatic mode and position the x-axle to that level. Run the step. Save and validate this step. Lower the speed so it's easier to achieve an angle of 120 degrees upon moving the joystick and moving the R-axle forward. During the bending process, do some measurements to check the angle obtained. After achieving 120 degrees, raise the speed to 100% and save the step. Place the X-axle again in the clamp position and save this step. Move the tube to the start of the following curve. Save and validate this step. Copy the values of the X-axle of the first curve, 25.4, to the Y-axle to make the second curve. Run the positioning and save the step. Check the step information screen again. Now, let's look at step 7, feed rate of R-axis, 272.8. To create this second curve, move the R-axle forward in the opposite direction. Therefore, enter the value but as a negative number. Run the positioning and save the step. Put the Y-axle back in the clamp position and save the step. Move the piece back on the R-axle so it is completely centered in the machine, 1,890 millimeters. Save the step. Since the bend is minimal at the middle of the piece, you don't run any movements on the R-axle. Instead, position the X and Y axles to create the central 120-degree angle. Save. Save the program. Let's create another piece that's identical to the previous one to quickly see how we can do mass production. Place the machine in a horizontal position to make this piece more comfortably and quickly. Always bending in the same direction instead of doing so to the left and to the right. Thus, the weight of the piece will not condition the result, and the bending machine does not have to be installed in an area with immense ceiling height. Now, I'm going to demonstrate the benefit of working this way by bending a greenhouse with a triple arch. I'm going to bend a spiral in a 20 by 1.5 tube to make the inner part of a heat exchanger. For more safety when making small radiuses, you can create the first step at low speed to do the first turn. This way the material can be safely guided to prevent collisions. Once the tube exceeds this area, run the following step in the program at maximum speed. Let's bend another piece as a spiral, this time progressively, from a smaller radius to a larger one. The Narhesa CNC bending kit was designed to be coupled with the MC550 and MC650 bending machines at any time, even after purchase. You just need to install the kit on the machine and activate it in the software. These are the elements comprising the CNC bending kit: a left support mechanism for the photocell, the right support mechanism, 2 Allen screws, 2 distancing bushings, a round knob, a washer, a guide die, and a photocell with an M12 connector, an encoder set and 4 screws, an upper cover and 6 hex screws, a front MC550 CNC cover and 4 screws. As far as tools, you need a ratchet wrench with a 10 hex cup, an 8 Allen wrench, a 5 Allen wrench, a 4 Allen wrench, a 17 fixed wrench, a Phillips screwdriver, oblique cutting pliers, 4 plastic cable ties, and a nylon hammer. The first thing you have to do is turn off the machine by rotating the main switch to 0 position. Use an 8 Allen wrench to remove the 2 DIN 912 screws and insert the 2 distancing bushings in their place. Screw the left support mechanism for the photocell using the Allen wrench. Screw the photocell around the guide die, leaving the end to jut out slightly, and tighten the lock nut with a fixed 17 wrench. Place the washer in the round knob axle and screw it in to the guide die. If you want to work with the bending machine starting profiles on the left, you can install the right support mechanism on the other side of the machine. Remove the upper cover and secure with 6 flanged hex screws. To loosen them, use the ratchet wrench with a 10 cup. Remove the front cover on the bending machine by loosening the 4 flanged hex screws securing it. Loosen these 4 screws and remove the machine housing cover where you'll couple the encoder set. Using the oblique cutting pliers, cut the cable ties securing the photocell cable and extend it over the left side of the machine. Secure the encoder set with your hand and place it over the machine housing, securing it with 4 DIN 912 screws. Tighten securely with an Allen wrench. Connect the encoder connector to the connector that sticks out of the electrical panel, securing the connection with 2 plastic cable ties. Grab the end of the photocell cable. This connector has a fit that prevents it from being incorrectly connected. Thread the connector firmly. Put the front cover on the MC550 CNC. Release the encoder to be able to work comfortably. Place the upper cover on, moving the photocell cable through the groove and screw it in. The mechanical installation of the new CNC bending kit is now finished. Open the electrical panel and grab the Ethernet cable that comes with the machine. Cut the cable ties and connect the ends of the cable, one to the Ethernet connector on the machine stand and the other to the Ethernet connector on the PC. Go to the narhesa.com website, access the Assistance menu, and click on the link Remote Connection. This downloads the necessary software, so our technical assistance service can connect remotely to your machine and help you complete the setup. Contact us and our technicians will guide you step by step to make the necessary adjustments in the frequency drive. Under certain ambient light conditions, the photocell might not detect an object that enters the operating area as occurs here, where none of the LEDs activate. To calibrate, you must press the button built into the photocell body. Once calibrated, just bring your hand in at the working distance and check that the LEDs activate upon detecting your hand. Now we're going to see how to switch the side on which the photocell is installed on the MC650 CNC machine in order to insert profiles to be bent on the left side. Always turn off the power to the machine, rotating the switch to position 0. Unscrew the photocell connector. Using an Allen screwdriver, loosen the screws, securing the left photocell support mechanism until it can be removed from the machine. The right support mechanism for the photocell is completely symmetrical to the left. Therefore, just release the round knob, remove the washer, and remove the guide die with the photocell to install them in the right support mechanism. Using the Allen screwdriver again, firmly tighten the screws, securing the piece, and vertically adjust the position of the photocell. Using a ratchet wrench, loosen the 6 hex screws, securing the upper cover, and remove them. Release the encoder to be able to work comfortably. Remove the upper cover. Place the photocell cable in the groove on the right side and secure the upper cover. Connect the cable to the photocell, making sure to screw the connector in well. Put the encoder back in the rest position and turn on the machine power by turning the main switch. To activate this change from left to right in the software, close the pop-up window with the alarm and access Menu, Settings. Go to Parameter PG 2.4, Photocell Mounting Side. Switch from left to right. You also have to change the parameter PG 2.5, Material Input Side, from right to left. Go back to manual mode and turn off the power to the machine so the changes made will become effective. When you turn the power back on, you can work by inserting the profiles to be bent on the left side of the machine. If you like this video, subscribe to our channel. Let's keep moving forward.